Da-da-da. What you doing, puppy? What you doing? What a dog doing? What's going on, Ray? How's it going? Welcome in, dude. You're quick. All right, let me do a little intro here for the recording. All right. All right. Hello, everybody. My name is Mike, and I hope you're having a wonderful day. I don't say Mike, it's Michael. Hello, everybody. My name is Michael. Hope you're having a wonderful day so far, and welcome back to the channel. Today, we're going to be jumping back into C Programming, a Modern Approach, second edition by K.N. King. Today, we're going to be starting. Boom, 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 boom. Chapter 6, Loops. We're going to be reading Chapter 6, Loops, today. So I hope you guys are having a great day, and thanks so much for coming in, and welcome back in. It should be a great read. If you guys are interested in joining me for the live stream, I live stream almost every single day around 7 p.m. PST as I teach myself computer science and programming by reading books like these and doing live projects. Cool. My notes that you see on the right side of my screen and the notes that you see on the right side of my screen and the rest of the notes from the previous chapters can be found in the link below at my GitHub. Oh my gosh, that was so bad. Got to restart that one. The notes that you see on the right side of my screen can be found in can be found in my GitHub link down below. Oh my gosh, dude! I'm recording, so I got to get this little intro out of the way. This sucks. I hate doing this part. The notes that you see on the right side of my screen can be found in my GitHub link down below. Thank you so much for being here. Let's go ahead and get started. All right, that's good enough for me. All right, this should be a fun one today. Let's go ahead and get going. I'll probably read the entire chapter, or at least read like sections, and then I might go back through and do notes. I don't want it to be too long. I want to get through the reading within like an hour, hour and a half. All right, let's go for it. Chapter 6, Loops. A program without a loop and a structured variable isn't worth writing. Chapter 5 covered C's selection statements, if and switch. This chapter introduces C's iteration statements. Which allows us to set up loops. A loop is a statement whose job is to repeatedly execute some other statement, the loop body. In C, every loop has a controlling expression. Each time the loop body is executed in an iteration of the loop, the controlling expression is evaluated. If the expression is true, has a value that is not 0, the loop continues to execute. C provides 3 iteration statements, while, do, and for, which are covered in sections 6.1, 6.2, and 6.3 respectively. The while statement is used for loops whose controlling the while statement is used for loops whose controlling expression is tested before the loop body is executed. The do statement is used if the expression is tested after the loop body is executed. The for statement is convenient for loops that increment or decrement a counting variable. Section 6.3 also introduces the comma operator, which is used primarily in for statements. The last two sections of this chapter are devoted to C features that are used in conjunction with loops. Section 6.4 describes the break, continue, and go to statements. Break jumps out of the loop and transfers control to the next statement after the loop. Continue skips the rest of the loop iteration, and go to jumps to any statement within a function. Section 6.5 covers the null statement, which can be used to create loops with empty bodies. Cool. Again, I'm going to kind of go back through and do my notes at a later. I want to get through the reading. The while statement. Awesome, Ray. What's going on? Hey, Tan May, welcome back in. Good to hear from you again. Konu, how's it going? Appreciate you for coming on Twitch today. You're awesome. Thanks for joining me. All right. Let's go, boys. Backwards hat on. Let's cook. Okay. 6.1, the while statement. Of all the ways to set up loops in C, the while statement is the simplest and most fundamental. The while statement has the form while, expression, statement. The expression inside the parentheses is the controlling expression. The statement after the parentheses is the loop body. Here's an example. While I is less than n, I is equal to I times 2. Note that the parentheses are mandatory and that nothing goes between the right parentheses and the loop body. Some languages require the word do. When a while statement is executed, the controlling expression is evaluated first. If its value is non-zero, true, the loop body is executed and the expression is tested again. The process continues in this fashion. First testing the controlling expression, then executing the loop body, until the controlling expression eventually has the value 0. The following example uses a while statement to compute the smallest power. The following example uses a while statement to compute the smallest power of 2 that is greater than or equal to a number n. I is equal to 1, while I is less than n, I is equal to I times 2. Suppose that n has the value of 10. The following trace shows what happens when the while statement is executed. I is equal to 1. I is now 1. Is I less than n? Question mark? Yes. Continue. I equals to I times 2. So I is now 2. Well, is I less than n? Yes. Continue into the loop. We multiply I by 2 and set it back equal to I. I is now 4. Is I less than 10, which is n, right? 10. Yes. Continue. I doubles. I is now 8. Is it still less than 10? Yes. It doubles. It's 16. Is it less than 10? No. Exit the loop. Notice how the loop keeps going as long as the controlling expression, I is less than n, is true. When the expression is false, the loop terminates and I is greater than or equal to n as desired. Although the loop body must be a single statement, that's merely a technicality. If we want more than one statement, we can just use braces to create a single compound statement. While I is greater than 0, braces, printf, this statement, and then decrease I. Some programmers always use braces even when they're not strictly necessary. As a second example, let's trace the execution of the following statements, which displays a series of countdown messages. T minus integer and counting. Before the while statement is executed, the variable I is assigned to the value of 10. Since 10 is greater than 0, the loop body is executed, causing the message T minus 10 and counting to be printed and I to be decremented. The condition I is greater than 0 is then tested again. Since 9 is greater than 0, the loop body is executed once more. This process continues until the message T minus 1 and counting is printed and I becomes 0. The test I is greater than 0 then fails, causing the loop to terminate. The countdown example leads us to make several observations about the while statement. The controlling expression is false when a while loop terminates. Thus, when a loop control by the expression I is greater than 0 terminates, I must be less than or equal to 0. Otherwise, we'd still be executing the loop. The body of a while loop may not be executed at all, since the controlling expression is tested before the loop is executed. It's possible that the body isn't executed even once. If I has a negative or 0 value when the countdown loop is first entered, the loop will do nothing. A while statement can often be written in a variety of ways. For example, we could make the countdown loop more concise by decrementing I inside of the call to printf. Right? This will decrement I afterwards and use the current value of I within this actual statement or this line. Infinite loops. A while statement won't terminate if the controlling expression always has a non-zero value. In fact, C programmers sometimes deliberately create an infinite loop by using a non-zero constant as the controlling expression. While 1. A while statement of this form will execute forever unless its body contains a statement that transfers control out of the loop, break, go to, return, or calls a function that causes the program to terminate. Printing a table of squares. Let's write a program that prints the table of squares. The program will first prompt the user to enter a number n. It will then print n lines of output, with each line containing a number between 1 and n together with its square. This program prints a table of squares. Enter the number of entries in table. 5, 1, 1, 2, 4, 3, 9, 4, 16, 5, 25. Let's have the program store the desired number of squares in a table named n. Let's have the program store the desired number of squares in a variable named n. We'll need a loop that repeatedly prints a number I and its square, starting with I equal to 1. The loop will repeat as long as I is less than or equal to n. We'll have to make sure to add 1 to I each time through the loop. We'll write the loop as a while statement. Frankly, we haven't got much choice since the while statement is the only kind of loop we've covered so far. Here's the finished program. We're going to print a table of squares using a while statement. We're going to include the standard I/O, and we're going to write a main function with no parameters or arguments. We're going to have two variables, int and I and n. We're going to have two variables, int I and n. Printf, this program prints a table of squares with a new line. We're going to enter a table of entries with a scanf to receive the user input and save that value in n. I is equal to 1. So we're going to do while I is less than n, so we're going to start at 1 or equal to n. So we will perform an operation when we get to n as well. We're going to print a integer here, integer here. We're going to insert I and I times I. So I and then the square of I. And we're going to reserve 10 spaces here of field width. And then we're going to increase I and go into the next sequence of the loop. Afterwards, once we exit, we will return 0. Note how square.c displays numbers in neatly aligned columns. The trick is to use a conversion specification like %10d instead of just %d, taking advantage of the fact that printf write justifies numbers when a field width is specified. Summing a series of numbers. As a second example of the while statement, let's write a program that sums a series of integers entered by the user. Here's what the user will see. This program sums a series of integers. Enter integers 0 to terminate. 8, 23, 71, 5, 0 as the last one. The sum is 107. Clearly, we'll need a loop that uses scanf to read a number and then adds the number to a running total. Letting n represent the number just read and sum the total of all numbers previously read. Just read. Letting n represent the number just read and sum the total of all numbers previously read. We end up with the following program. Include standard I/O. We have int main void. We have int n and sum equals to 0. We're going to print. This program sums a series of integers and then a new line. We're going to print enter integers 0 to terminate, colon, space. We're going to scan for user input and save that in the value of n for the number of integers. while n is not 0, we're going to sum increases by n, and then scan f. We're then going to print the sum as this and then return after the loop. Notice that the condition n is not equal to 0 is tested just after the number is read, allowing the loop to terminate as soon as possible. Also note there are two identical calls of scanf, which is often hard to avoid when using while loops. So how does this work then? I'm a little confused because you just give a list of numbers altogether. Or maybe this is a little misleading, like maybe it's looping, right? If we actually wrote this out, it might be looping, reprompting with the scanf. Yeah, because it's printing this, and then you enter a number. How's it going, Rusty Huts? How's it going? Appreciate you coming in. Oh, Sean Wave. Yo, what's going on? Appreciate the kind words. This book is called C Programming, A Modern Approach, second edition by Kay and King. I got a link to a lot of information in my Discord for free, link down below, or you can just look it up online. It's pretty easy to find. It's a different camera angle than before or something. I think it's the same one. Got a new camera angle or something? Let me grab some water real quick, and we'll keep going. So, can someone explain to me, right, why, like, what's going on here, but before we, unless we just need to write it? Because, so, our while loop is here, and we're scanning, I guess, so it'll just print this once then, I think. It'll print this once. And then continually scan for you to enter numbers, and then you enter 0, and then you print the sum at the end. It's not like you print numbers with spaces in them, right? Let me go grab some water real quick, and we'll move on to 6.2. All right. Okay. All right. Let me see here. Let me take this guy here. Well, I think it'd probably be better for us to just, might be kind of annoying, but let's just, I don't care. Sum.c. Let's just be quick. So include the each. Let's go ahead and open this up. \n. Okay, let's go printf, enter, teachers. And let's go scanf. Let's save this in a integer here. I'll go %n. Wow. And not equal to 0. Right, we're going to open this up and sum plus equals n and scanf and get a new value. Save it %d and here. Override the value of n with a new value. And then we're going to printf here. The sum is, and then do return 0. Okay. So let's see if we can run this bad boy here. Here we go. So GCC chapter 6. Yeah. No. Right, we do this. That guy. Okay, so if we say 5, 6, 7, yeah, okay. Well, now give me that one. I didn't like the float, I don't think. We gave it a float, didn't like it. Try again. Okay, that's it. So it just will. The scanf has a \n kind of already associated with it, right? So that's why it goes to a new line. Got you. I was just wondering, like, where, if it was prompting every single time or how it was actually running under the hood here. So that's cool. That's cool. Fun, 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 fun. Okay, let's keep pushing. I'll come back and fill in the notes. I want to just get through the reading here before it gets too late. For those that don't know, for those that are new here, my name is Michael. Thanks so much for joining me here. I have a degree in human biology and a minor in chemistry. I'm 26 years old, and I graduated back in 2022. I work as a chemist, and I've been teaching myself Python and computer science and now C now for the past year and a half. almost every single day after work, and it's been pretty. I'm feeling it, boys. I'm feeling the burn. But we grind and we grind on. We grind on. Keep going. Good thing is the kind of those that keep grinding. I don't know. I have this belief that we just keep pushing. One of these something will happen. I don't know. Might be this false belief. Whatever. Let's keep pushing. 6.2, the do statement. The do statement is closely related to the while statement. In fact, the do statement is essentially just a while statement whose controlling expression is tested after a The do statement is closely related to the while statement. In fact, the do statement is essentially just a while statement whose controlling expression is tested after each execution of the body. After each execution of the loop body. The do statement has the form do statement while expression. As with the while statement, the body of the do statement must be one statement, possibly compound, of course, and the controlling expression must be enclosed within parentheses. When a do statement is executed, the loop body is executed first, then the controlling expression is evaluated. If the value of the controlling expression is zero, if the value of the expression is non-zero, the loop body is executed again, and then the expression is evaluated once more. Execution of the do statement terminates when the controlling expression has the value 0 after the loop body has been executed. Let's rewrite the countdown example of section 6.1 using a do statement this time. I is equal to 10. Do printf t minus number and counting, insert I, and then decrease I in this line, while I is greater than 0. So do this action, then decrease I, evaluate this. If that's true, then go back and keep going. Else, just keep moving on. So I guess maybe with the do statement is no matter what, you at least hit at one time, potentially. Is that like a caveat here? When the do statement is executed, the loop body is first executed, causing the message t minus 1 and counting to be printed and 1 to be decremented. The condition I greater than 0 is now tested. Since 9 is greater than 0, the loop body is executed a second time. This process continues until the message t minus 1 and counting is printed and I becomes 0. The test I is greater than 0 now fails, causing the loop to terminate. As this example shows, the do statement is often indistinguishable from the while statement. The difference between the two is that the body of a do statement is always executed at least once. The body of a while statement is skipped entirely if the controlling expression is 0 initially. Boom, we got that spot on. Incidentally, it's a good idea to use braces in all do statements, whether or not they're needed, because a do statement without braces can easily be mistaken for a while statement. Do this, while that. A careless reader might think the word while was the beginning of a while statement. Cool, we got that spot on. Program. Calculating the number of digits in an integer. Although the while statement appears in C programs much more often than the do statement, the latter is handy for loops that must execute at least once. To illustrate this point, let's write a program that calculates the number of digits in an integer entered by a user. Enter a non-negative integer, 60. The number has 2 digits. Our strategy will be to divide the user's input by 10 repeatedly until it becomes 0. The number of divisions performed is the number of digits. Clearly, we'll need some kind of loop since we don't know how many divisions it will take to reach 0. But should we use a while statement or a do statement? The do statement turns out to be more attractive because every integer, even 0, has at least 1 digit. Here's the program. Calculates the number of digits in an integer. Include standard io.h. Int main void. Int digits is equal to 0 and we have an integer n. Printf, enter a non-negative integer, and we'll scan and read that into n. Do n divided by n is equal to 10, and then we increase digits. So this will increase digits after the execution. So while n is greater than 0, got you. To see why the do statement is the right choice, let's see what would happen if they were to replace the do statement by a similar while loop. While n is greater than 0, n divided equals by 10 digits plus plus. If n is initially 0, this loop won't be executed at all, and the program would output the number has n. The number has 0 digits. Could you not just do greater than or equal to? And wondering why a what do while is used if we could just make the while condition greater than or equal to 0 instead of n is greater than 0. The original do while approach, do n divided by 10 and then increase the number of digits count as many times as n is greater than 0. Why it works. Do while guarantees that the loop body executes at least once even if n is 0. So if the user enters 0, the digits become 1, which is correct. 0 has 1 digit. What happens if you try n is greater than or equal to 0 instead? Problem, if n is greater than 0, this will never terminate correctly. Why? Oh, because it never goes down past 0 in this problem. You're not decrementing n down. You're just dividing it by 10, which will floor eventually to 0 and stop there. You won't actually ever get. Now you could throw a flag maybe and say if n equals to 0 break, but maybe just do the do while instead. Okay, gotcha. So hold on, let's see if it can even hear me. No. Okay. That's right. Because the n will stop at 0 and not go negative. So the condition is always true. We would need to flag n equals to 0 and break, but just do the do while probably. If you tried while n is greater than or equal to 0, n would eventually hit 0 and never become negative, so the loop would never end or run forever. You could add a special check inside the loop if n is equal to 0 break, but that's basically reinventing the do while, which is already done. Cool. And then let's go here. 6.3, the for statement. We now come to last of C's loops, the for statement. Don't be discouraged by the for statement's apparent complexity. It's actually the best way to write many loops. The for statement is ideal for loops that have a counting variable, but it's versatile enough to be used for other kinds of loops as well. The for statement has the form for expression 1, expression 2, expression 3, statement. where expression 1, expression 2, and expression 3 are expressions. Here's an example. For I is equal to 10, I is greater than 0, I minus minus, printf, t minus integer and counting, insert I. When this for statement is executed, the variable I is initialized to 10. Then I is tested to see if it's greater than 0. Since it is, the message t minus 10 and counting is printed, and then I is decremented. The condition I is greater than 0 is then tested again. The loop body will be executed 10 times in all, with I varying from 10 down to 1. The for statement is closely related to the while statement, in fact, except in a few rare cases, a for loop can always be replaced by an equivalent while loop. Expression 1, while expression 2, statement, expression 3. In this pattern, as this pattern shows, expression 1 is an initialization step that performs only once before the loop begins to execute. Expression 2 controls the loop termination. The loop continues executing as long as the value of expression 2 is non-zero. And expression 3 is an operation to be performed at the end of each loop iteration. Applying this pattern to our previous for loop example, we arrive at the following. I equals to 10, while I is greater than 0, we print out the message and then decrease I. Studying the equivalent while statement can help us understand the fine points of a for statement. For example, suppose that we replace I minus minus by minus minus I in our for loop example. For I is equal to 10, while I is greater than 0, less than I. Printf t minus insert I and counting. How does this change affect the loop? Looking at the equivalent while loop, we see that it has no effect. Right, I will be minus in this line and then just reverted back. Whereas in the previous example, I is minus after the execution of this loop and receives the new value of I later on. Since the first and third expression in a for statement are executed as statements, their values are irrelevant. They're useful only for their side effects. Consequently, these two expressions are usually assignments or incremented/decremented expressions. For statement idioms. The for statement is usually the best choice for loops that count up, increment a variable, or count down, decrement a variable. A for statement that counts up or down a total of n times will usually have one of the following forms. Counting up from 0 to n minus 1. For I is equal to 0, I is less than n, I plus plus. Counting up from 1 to n. For I is equal to 1, I less than or equal to n, I plus plus. Counting down from n minus 1 to 0. For I is equal to n less than 1, while I is greater than or equal to 0, I minus minus. Counting down from n to 1. For I is equal to n, while I is greater than 0, decrease I. Imitating these patterns will help you avoid some of the following errors which C programmers often. Gosh. Let me get a drink here. Imitating these patterns will help you avoid some of the following errors which beginning C programmers often make. Using less than instead of greater than, or vice versa in the controlling expression. Notice that counting up loops use the less than or less than to equal to operator, while counting down rely on the inverse. Using is equal to in the controlling expression instead of less than equal to, greater than or equal to. A controlling expression needs to be a true statement at the beginning of the loop, then later become false so that the loop can terminate. A test such as I is equal to n doesn't make much sense because it won't be true initially. Off by one errors, such as writing the controlling expression I is less than or equal to n instead of I is less than n. Omitting expressions in a for statement. The for statement is even more flexible than we've seen so far. For for loops, some for loops may not need all three of the expressions that normally control the loop, so C allows us to omit any or all of the expressions. If the first expression is omitted, no initialization is performed before the loop is executed. I is equal to 10 for blank colon. So you still need to put the semicolons then. I is equal to 10 for semicolon. I greater than 0 semicolon less than I. In this example, I has been initialized by a separate assignment, so we've omitted the first expression in the for statement. Notice that the semicolon between the first and second expression remains. The two semicolons must always be present, even when we've omitted some of the expressions. If we omitted the third expression in a for statement, the loop body is responsible for ensuring that the value of the second expression eventually becomes false. If we omit the third expression in our for statement, the loop body is responsible for ensuring that the value of the second expression eventually becomes false. Our for statement example could be written like this. For I is equal to 10, loop while I is greater than 0, with no incrementing or decrementing happening to I. We could decrement I and increment it, or we need to, in the loop body. To compensate for omitting the third expression, we've arranged for I to be decremented inside the loop body. When the first and third expressions are both omitted, the resulting loop is nothing more than a while statement in disguise. For example, the loop for semicolon I greater than 0 semicolon print this I less is the same as while I is greater than 0 print this I less. The while version is cleaner and therefore preferable. If the second expression gosh, I got like the hiccups or something. If the second expression is missing, it defaults to a true value, so the for loop statement doesn't terminate unless stopped in some other fashion. For example, some programmers use the following for statement to establish an infinite loop. For semicolon. For statements in C99. In C99, the expression in a for statement can be replaced by a declaration. This feature allows the programmer to declare a variable for use in the for loop. For int I is equal to 0, I is less than n, I plus plus. The variable I need not be declared prior to this statement. In fact, if a declaration of I already exists, this statement creates a new version of I that will be used solely within the loop. A variable declared by a for statement can't be accessed outside the body of the loop. We say this is not visible outside of the loop. For int I is equal to 0, I is less than n, I plus plus, print the number I is visible inside the loop. If we print I outside the loop, this is wrong. Having a for statement declare its own control variable is usually a good idea. It's convenient and it can make programs easier to understand. However, if the program needs to access the variable after the loop termination, it's necessary to use the older form of the for statement. Incidentally, a for statement may declare more than one variable provided for. Incidentally, a for statement may declare one or more than one variable. Incidentally, a for statement may declare more than one variable provided that all variables have the same type. For int I equals 0, j equals 0, I is less than n, I plus plus. Cool. The comma operator. On occasion, we might like to write a for statement with two or more initialization expressions, or one that increments several variables each time through the loop. We can do this by using a comma expression as the first or third expression in the for statement. A comma expression has the form of expression 1, comma, expression 2, where expression 1 and expression 2 are two expressions. A comma expression is evaluated in two steps. First, expression 1 is evaluated, and its value is discarded. Second, expression 2 is evaluated. Its value is the value of the entire expression. Evaluating expression 1 should always have a side effect. If it doesn't, then expression 1 serves no purpose. For example, suppose that I and j have the values 1 and 5 respectively. When the comma expression I plus j is evaluated, I is first incremented, then I plus j is evaluated. So the value of the expression is 7. And of course, I now has the value of 2. The precedence of the comma operator is less than that of all other operators, by the way. So there's no need to put parentheses around plus I and I plus j. Occasionally, we'll need to chain together a series of comma expressions, just as we sometimes chain assignments together. The comma operator is left associative, so the compiler interprets I equals to 1, comma, j equals to 2, comma, k equals to j plus k equals to j plus I. Oh my gosh. I equals to 1, j equals to 2, k equals to I plus j, as all wrapped in parentheses with each sub-expression wrapped in parentheses. Gotcha. Yeah, okay. So it'll go in, it'll perform this one, and then it'll perform this one, and then assign that to k. Since the left operand in a comma expression is evaluated before the right operand, the assignment I is equal to 1, j is equal to 2, and k equals to I plus j will be performed from left to right. The comma operator is provided for situations where C requires a single expression, but we'd like to have 2 or more expressions. In other words, the comma operator allows us to glue 2 expressions together to form a single expression. Note the similarity to the compound statement, which allows us to treat a group of statements as a single statement. The need to glue expressions together doesn't arise that often. Certain macro definitions can benefit from the comma operator, as we'll see in later chapters. The for statement is the only other place where the comma operator is likely to be found. For example, suppose that we want to initialize 2 variables when entering a for statement. Instead of writing sum equals to 0, for I is equal to 1, I less than capital N, I plus plus, sum plus equals to I, we can write for sum is equal to 0, I is equal to 1, I is less than or equal to N, I plus plus, sum plus equals to I in the loop body. The expression sum equals to 0, I equals to 1 first assigns 0 to sum, then assigns 1 to I with additional commas. The for statement could initialize 2 or more than 2 variables. With additional commas, the for statement could initialize more than 2 variables. Printing a table of squares revisited. The square.c program, section 6.1, can be improved by converting its while loop to a for loop. Print a table of squares using a for statement. Include standard io.h, int main void, int I and n, printf. This program prints a table of squares. We are then going to print enter a number of entries in the table. We're then going to scanf for the integer value and save it into n. I is going to initialize to 1, while I is less than or equal to n in this for loop. We're going to increase I after the loop body. So printf, we're going to print our statement here and insert the 2 values I and I times I. We're then going to increase I and then do this evaluation I less than or equal to n. We can use this program to illustrate an important point about the for statement. C places no restrictions on the 3 expressions that control its behavior. Although these expressions usually initialize, test, and update the same variable, there's no requirement that they be related in any way. Consider the following version of the same program. Prints a table of squares using an odd method. Int I, n, odd, and square. So enter a number of entries in the table. I is equal to 1 and odd is equal to 3. For square is equal to 1, while I is less than or equal to n, odd plus equals 2. We would print the square value, insert I in the square, and then increase I. and then increase the square by odd, and then return. So there's a different way of doing it. The for statement in this program initializes one variable square, tests another I, and increments a third odd. I is the number to be squared, square is the square of I, and odd is the odd number that must be added to the current square to get to the next square, allowing the program to compute consecutive squares without performing any multiplications. The tremendous flexibility of the for loop sometimes can be useful. The tremendous flexibility of the for statement can sometimes be useful. We'll find it to be a great help when working with linked lists. The for statement can easily be misused though, so don't go overboard. The for loop in square3.c would be a lot cleaner if we rearranged its pieces so that the loop is clearly controlling. I cannot read, dude. The for loop in square3.c would be a lot cleaner if we rearrange its pieces so that the loop is cleanly controlled by I. 6.4, exiting from a loop. Again, I'll go back through and take notes probably a little bit later, like after some time goes by, to let it kind of sit, and then I'll come back and take some notes to revisit the material. Just because I want to get through the reading here before the night gets too long. Hey, it's going One Straw Hat. Welcome in. This is just independent learning here. Can't stay long tonight, but I have to say, love what you're doing here, man. Electrical electronics engineer. You've got to gain a sub new like. Thanks, dude. I appreciate you. Thanks, Ant6. That's awesome. It's great to meet you. Yeah, we on chapter 6 now. We flying. Honestly, it doesn't feel like we're getting very far, but we're moving, I guess. We're already on page 136 at 8:30 here. So, chapter 6. We're finally getting to loops and a couple more things. Once you get past pointers and memory, then we can start kind of writing maybe some of our own little beginner scripts and stuff, or in C. Some of our own stuff. Yeah. Okay, 6.4, exiting from a loop. We've seen how to write loops that have an exit point before the loop body using while and for statements, or after it using do statements. Occasionally, however, we'll need a loop with an exit point in the middle. We may even want a loop to have more than one exit point. The break statement makes it possible to write either kind of loop. After we have examined the break statement, we'll look at a couple of related statements, continue and go to. The continue statement makes it possible to skip part of a loop iteration without jumping out of the loop. The go-to statement allows a program to jump from one statement to another. Thanks to the availability of statements such as break, continue, and go-to statements is rarely used. Oh, hold on. The go-to statement allows a program to jump from one string. The go-to statement allows a program to jump from one statement to another. Thanks to the availability of statements such as break and continue, the go-to statement is rarely used. The break statement. We've already discussed how a break statement can transfer control out of a switch statement. The break statement can also be used to jump out of a while, do, or for loop. Suppose that we're writing a program that checks whether a number n is prime. Our plan is to write a for statement that divides n by the numbers between 2 and n minus 1. We should break out of the loop as soon as any divisor is found. There's no need to try the remaining possibilities. After the loop has terminated, we can use an if statement to determine whether termination was premature, hence n isn't prime, or normal, n is prime. For d is equal to 2, d is less than n, d++, if n divided by d is equal to 0, if the remainder of n divided by d is equal to 0, then break. If n is less than, so then, is this outside of the loop? Yeah. If d is less than n, print the integer is divisible by this integer. Else, print the integer is prime. Got you. So you're just testing to see if there's a remainder given the value, of primes up to some value, right? So d is initially 2 up to some value of n. So you start at 2, go up to some value of n, and increase d each time. You're going to do n divided by d and compute the remainder, right? So that if it's 0, then you know you found a um, so if it's 0, we break out immediately, meaning that you found a prime number here. Or sorry, you're divisible, and then else is a prime number. Okay. The break statement is particularly useful for writing loops in which the exit point is in the middle of the body rather than at the beginning or end. Loops that read user input, terminating when a particular value is entered, often fall into this category. So we're going to have an infinite loop here, for, and we're going to print, enter a number, enter 0 to stop. We're going to continually scan. If n is equal to 0, break. We're going to print the integer cubed is n, and then n times n times n. So why would you do this? Like, you infinitely go until the user enters 0. Oh, and you just print cubes. You print the cubes until you enter 0. Got you. A break statement transfers control out of the innermost enclosing while, do, for, or switch statement. Thus, when these statements are nested, the break statement can escape only one level of nesting. Consider the case of a switch statement nested inside a while statement. Switch with a break inside. Nested all within a while loop. The break statement transfers control out of the switch statement but not out of the while loop. I'll return to this at a later point. The continue statement. The continue statement doesn't really belong here because it doesn't exit from a loop. It's similar to break though, so its inclusion in this section isn't completely arbitrary. Break transfers control just past the end of a loop, while continue transfers control to a point just before the end of the loop body. With break, control leaves the loop. With continue, control remains inside the loop. There's another difference between break and continue. Break can be used in switch statements and loops, while do and for, whereas continue is limited to loops. The following example, which reads a series of numbers and computes their sum, illustrates a simple use of continue. The loop terminates when 10 non-zero numbers have been read. Whenever the number 0 is read, the continue statement is executed, skipping the rest of the loop body. The statement sum plus equals to I and n plus plus, but remaining inside of the loop. So we set n equals to 0 and sum is equal to 0. While n is less than 10, we're going to read input and save that value in I. If I is equal to 0, we're going to continue and not increase the sum by I and not increase n. Right, so this kind of says, like, it's definitely right. I think about it a little differently, which I'm not sure if the way I think about it is wrong or right. I think it's like the same type of thinking, it's just a little bit of a different way of thinking about it. This is kind of saying like the continue statement will jump to the end of the loop and then continue the loop over. I like to think of the continue statement as once you hit the continue, you just jump right back to here. Um, and you start over again. Now, because you actually didn't do anything, right? You didn't actually increase n or do anything to n. There is no actually the evaluation of that same conditional is the same, and you just keep going, right? But it's the same thing. It would just jump right before it starts over again, which is the same place as like right here in my mind, right? Like as you're going left to right, it's kind of continues right to there, which kind of goes to the end and then wraps to here. So it's the same thing, yeah. If continue were not available, we could have written the example as follows, right? If I is not equal to 0, then we'll go ahead and do this rather than continuing a loop. The go-to statement. Break and continue are jump statements that transfer control from one point in the program to another. Both are restricted. The target of a break is a point just beyond the end of the enclosing loop, while the target of continue is a point just before the end of the loop. The goTo statement, on the other hand, is capable of jumping to any statement in a function provided that the statement has a label. C99 places an additional restriction on the goTo statement. It can't be used to bypass the declaration of a variable length array. A label, which comes up in 8.3. A label is just an identifier placed at the beginning of a statement. Identifier colon statement. A statement may have more than one label. The goTo statement itself has the form goTo identifier. Executing the statement goTo capital L transfers the control to the statement that follows the label L, which must be in the same function as the goTo statement itself. If C didn't have a break statement, here's how we might use a goTo statement to exit prematurely from a loop. For d is equal to 2, d is less than n, d plus plus. If the remainder of n divided by d is equal to 0, goTo done. Done, colon, if d is less than n, print the number is divisible by the number, else print the number is prime. Got you. So you can just specify a label with whatever statements you want to happen after that jump point, basically. The goTo statement, a staple of older programming languages, is rarely needed in everyday C programming. The break, continue, and return statements, which are essentially restricted goTo statements, and the exit function are sufficient to handle most situations that might require a goTo in other languages. Nonetheless, the goTo statement can be helpful once in a while. Consider the problem of exiting a loop from within a switch statement, as we saw earlier. The break statement doesn't quite have the desired effect. It exits from the switch, but not the loop. A goTo statement solves this problem. While with a nested switch, if we have a goTo loop done, it'll jump to the loop done outside of the while. The goTo statement is also useful for exiting from nested loops. Program, balancing a checkbook. Many simple interactive programs are menu-based. They present the users with a list of commands to choose from. Once the user has selected a command, the program performs the desired action, then prompts the user for another command. This process continues until the user selects an exit or quit command. The heart of such a program will obviously be a loop. Inside the loop will be statements that prompt the user for a command, read the command, then decide what action to take. We have an infinite loop here. Prompt the user for a command, read the command, and execute the command. Executing the command will require a switch statement or cascaded if statement. For infinitely, prompt the user to enter a command, read the command, switch on that command with a case for the command, and perform operation and then break, with many other cases to do, and then a default for an error message. To illustrate this arrangement, let's develop a program that maintains a checkbook balance. The program will offer the user a menu of choices: clear the account balance, credit money to the account, debit money from the account, display the current balance, and exit the program. The choices are represented by the integers 0, 1, 2, 3, and 4, respectively. Here's what a session with the program will look like. ACME checkbook balancing program. Commands: 0 equals clear, 1 equals credit, 2 equals debit, 3 equals balance, 4 equals exit. Command enter 1, amount of credit equals this. Enter command 2, amount of debit. Enter amount of debit is this. Enter command 1, enter amount of credit. Enter command 2, amount of debit, so on and so forth until we enter a balance, and then we quit. When the user enters the command 4, exit, the program needs to exit from the switch statement and the surrounding loop. The break statement won't help, and we prefer not to use the goTo statement. Instead, we'll have the program execute a return statement, which will cause the main function to return to the operating system. So here's how we would write the function. Int main void. We have an int variable for CMD, and we have a float, which is a balance set to 0, and then credit and debit with no declaration, or with no initialization. We have the print statements. And then we have our loop here. To enter command, we scan for the command. We have a switch statement over the command. For each case, we have these cases to do. If we hit case 4, we have a return to the operating system. And then our default case is to reprint these and then break out of the switch statement, causing the loop to enter again. Note that the return statement is not followed by a break statement. A break immediately following a return can never be executed, and many compilers will issue a warning message. Hey yo, Mr. John, welcome back in today. I know, dude, I've been missing loops from I've been in these practice problems we've done up through chapter 5. We haven't had access to loops, so I've been kind of being honest to the book. Yes, we've done loops in Python, and we've had lots of experience writing loops in Python and whatnot in this year and a half of learning. But I've been trying to be honest to the book's learning so far, and up through chapter 6 so far. And so now we're finally putting in that infinity stone into our C gauntlet here. This is the C gauntlet. We'll have to put in that. Yeah. Yo, so thanks for coming in. I appreciate you guys being here. We got like 25 people in here. If you guys could leave a like if you're enjoying the reading. My throat's getting raspy here, guys. Leave a like for the raspy throat. Pause. Leave a like, you guys. I appreciate you being here. My name is Michael. I'm a formulation chemist. I have a degree in human biology and a minor in chemistry, and I work as a chemist. I stream almost every single day, reading books like this, coding live, doing live projects, chemistry, biology projects, finance projects, stock option projects, all from scratch. I don't copy any of my projects from. I don't do any of that. All my projects are original, with just some minor help from resources I find online. And yeah, it's cool so far. Here we go. Let's keep pushing. 6.5, the null statement. A statement can be null. Oh, hold on. We're going to have a lot of notes to come back to. A statement can be null, devoid of symbols except for the semicolon at the end. Here's an example. I is equal to 0, colon, nothing, colon, j is equal to 1, colon. This line contains 3 statements, an assignment to I, a null statement, and an assignment to j. The null statement is primarily good for one thing, writing loops whose bodies are empty. As an example, recall the prime finding loop of section 6.4. For d is equal to 2, d less than n, d plus plus, if the remainder of n divided by d is 0, then break. If we move the n divided remainder d is equal to 0 condition into the loop's controlling expression, the body of the loop becomes empty. For d is equal to 2, d is less than n, and the remainder of n divided by d is not equal to 0, d plus plus. Each time throughout the loop, the condition d is less than n is tested first. If it's false, the loop terminates. Otherwise, the condition n divided by d, the remainder of n divided by d is not equal to 0 is tested. And if that's false, the loop terminates. In the latter case, n modulo d is equal to 0 must be true. In other words, we've found a divisor of n. Note how we've put the null statement on a line by itself instead of writing this. C programmers customarily put the null statement on a line by itself, otherwise someone reading the program might get confused about whether the statement after the for was actually its body. So you can see that they wrapped that colon down to show that you might get confused, you're thinking that this is a part of the for loop body if you don't read this trailing colon. Converting an ordinary loop into one with an empty body doesn't buy much. The new loop is often more concise, but usually no more efficient. In a few cases, Gosh, dude. Okay, sorry, guys. Converting an ordinary loop into one with an empty body doesn't buy much. The new loop is often more concise but usually no more efficient. In a few cases, though, a loop with an empty body is clearly superior to the alternatives. For example, we'll find these loops to be handy for reading character data in section 7.3. Accidentally putting a semicolon after the parentheses in an if, while, or for statement creates a null statement, thus ending the if, while, or for prematurely. In an if statement, putting a semicolon after the parentheses creates an if statement that apparently performs the same action regardless of the value it's controlling expression. In an if statement, putting a semicolon after the parentheses creates an if statement that apparently performs the same actions regardless of the value of its controlling expression. If d is equal to 0, colon, wrong, right? Print this. This will actually never happen because the loop ends in this statement here. The printf isn't inside the if statement, so it's performed regardless whether d is equal to 0. Oh, sorry. I said that wrong. So the printf, will be printed regardless because it's not associated with this if statement. In a while statement, putting a semicolon after the parentheses may create an infinite loop. So if you say while I is greater than 0, semicolon, I remains, as 10 here, and this never gets executed within this here. Well, would this get executed? Let's look this up really quick. See if I can fix this. Because the semicolon. And then it has this. The classic C trap, a semicolon terminates the loop. So the loop body block is not part of the loop. The loop runs infinitely doing nothing. Then your block runs once afterwards. Yeah. Another possibility is that the loop terminates, but the statement that should be the statement that should be the loop body is executed only once after the loop has terminated. I is equal to 11, while minus minus I is greater than 0, semicolon. So the print does happen because I minus minus is greater than 0. So the print happens once. But after the loop has taken place and reduced I all the way down to 0, right? So this loop happens, reduces I all the way down, and then we print out 0 here within this insertion. In a for statement, putting a semicolon after the parentheses causes the statement that should be in the loop body to be executed only once. So we would say for this expression, right, I is equal, it gets initialized to 10. It gets reduced down and checked at each time. So the loop does take place and happens, and then this print statement happens, printing out the resulting I, which is 0. But I thought that this I thought that I is restricted to the for loop. Infinite loop condition. It had to be declared before. So then you knew we do it inside. I only exists inside the loop. Outside the loop is identified. So it would be in here. So in the incorrect example, why does it still print 0 for I? Semicolon after the loop. The semicolon means the loop has an empty body. The loop executes I minus minus repeatedly, but does not do anything else inside the loop. Infinite loop problem with I greater than 0. Well, this should be just I. The loop runs. After the last iteration becomes 0, the loop stops, then prints. Printing once, printing 0. So the reason it prints 0 is because the loop does all the decrement, but it has no code inside the loop. After the loop ends, I has reached 0, and that's what gets printed. Again, but I thought that I in the loop that decreases to 0 stays in the loop scope. How can we access it in the new line, right? You thought that I declared in a for loop only exists inside the loop, but you still want to access it afterwards. Declare the scope of the rules in C. Declaring I inside the for loop. Here, I is local inside the loop. Once I ends, I does not exist outside. Trying to access it gives a compile runtime error. But if you were to declare it outside, and then okay, because I think it's abstracting the declaration of int I outside of the for loop somewhere. And so, because I is established outside of the loop and then accessed and initialized inside of the loop, it still remains a 0 in the like mother scope of the entire program. But it's just in this little code snippet, it's abstracted away. Oh, because, well, they don't have it in there either. So I think they're just abstracting it away, John. Yeah, it's either a typo or I mean it's a little bit confusing. They probably should put the declaration of the variable, you know. Uh, so the book in the example is just abstracting away the int I declaration outside the loop above and using that bar. Many textbooks abstract away the variable declaration. Okay. Yeah, it's kind of like, oh, chill. No, John, why'd you make me do that? No, John. Oh. Tomato, tomato. It's like I don't know. It's like 50-50. It's like, it's for some people might get it, some people not. It's like I don't know. All right, cool. Let's just bust out this Q&A real quick. Let's keep pushing. And then we'll be done here. Question. The following loop appears in section 6.1. While I is greater than 0, print t minus integer and counting, insert I less than printf t minus integer and counting, I less less. Why not shorten the loop even more by removing the greater than 0 test? While I then print. This version will stop when I reaches 0, so it should be just as good as the original. Answer: the new version is certainly more concise, and many C programmers would write the loop in just this way. It does have its drawbacks, though. First, the new loop is not as easy to read as the original. It's clear that the loop will terminate when I reaches 0, but it's not obvious whether you're counting up or down. In the original loop, that information can be deduced from the controlling expression I greater than 0. Second, the new loop behaves differently than the original if I should happen to have a negative value when the loop begins to execute. The original loop terminates immediately, but the new loop does not. Question: 6.3 says that, except in rare cases, for loops can be converted to while loops using a standard pattern. Can you give an example of such a case? Answer: when the body of a for loop contains a continue statement, the while pattern shown in section 6.3 is no longer valid. Consider the following example from section 6.4, where we have n is equal to 0, sum is equal to 0. While n is less than 10, scanf and save that value into I. If I is equal to 0, we continue. Right? Else we sum increase by I and increase n and increase n. At first glance, it looks as though we could convert the while loop into a for loop. Unfortunately, this loop isn't equivalent to the original. When I is equal to 0, the original loop doesn't increment n, but the new loop does. Yeah. Which form of infinite loop is preferable, while 1 or for semicolon semicolon? C programmers have traditionally preferred for semicolon semicolon for reasons of efficiency. Older compilers would often force programs to test the one condition each time through the while loop, while with modern compilers, however, there should be no difference in performance. Question: I've heard that programmers should never use the continue statement. Is this true? It's true that continue statements are rare. Still, continue is handy once in a while. Suppose we're writing a loop that reads some data. Suppose that we're writing a loop that reads some input data, checks that it's valid, and if so, processes the input in some way. If there are a number of validity oh my gosh. If there are a number of validity tests, or if they are complex, continue can be helpful. The loop would look something like this: for infinitely, read the data. If data fails the first test, then continue. If data fails the second test, then continue. If data fails the third test, then continue, else process data. What's so bad about goto statement? The goto statement isn't inherently evil. It's just that we usually have better alternatives. Programs that use more than a few goto statements can quickly degenerate into spaghetti code. Programs that use more than a few goto statements can quickly degenerate into spaghetti code, with control blithely jumping from here to there. Spaghetti code is hard to understand and hard to modify. Goto statements make programs hard to read because they jump either forward or backward. In contrast, break and continue only jump forward. A program that contains goto statements often requires the reader to jump back and forth in an attempt to follow the flow of control. Goto statements can make programs hard to modify, since they make it possible for a section of code to serve more than one purpose. For example, a statement that's preceded by a label might be reachable either by following through from the previous statement or by executing one of several goto statements. Question: does the null statement have any uses besides indicating that the body of a loop is empty? Answer: very few. Since the null statement can appear wherever a statement is allowed, There are many potential uses for the null statement. In practice, however, there's only one other use for the null statement, and it's rare. Suppose that we need to put a label at the end of a compound statement. A label can't stand alone. It must always be followed by a statement. Putting a null statement after the label solves the problem. Question: are there any other ways to make an empty loop body stand out besides putting the null statement on a line by itself? Some programmers use a dummy continue statement. For some expression, continue. Others use an empty compound statement. And we finally reached the exercises. Woo! That was a lot. Read for an hour and a half straight. Woo! That was like 25 pages of C programming books going over loops. Now, we got to go back through, obviously, and go through and take some notes, but um, I think I'm going to probably let me go ahead and wrap up this. I'm not going to wrap up the stream yet. Let me wrap up the recording though. All right, hold on real quick. Let me go back up to the top here, chapter 6. This is chapter 5. All right, everybody. This was chapter 6 of C Programming: A Modern Approach, second edition by K.N. King. Chapter 6, Loops. Had a lot of fun reading this one. I'm going to go back through and take some notes here in the next session. And you guys can get access to these in my GitHub link down below. Thanks so much for watching, and I'll see you guys in the next one. All right, I'll stop the recording there. Boom. Nebula Shadow, welcome. Hello, buddy. Just found your stream. I have a test coming up on C programming. Your stream is helpful. Nice, dude. Yeah, I highly suggest you take. I've really condensed down the reading into, got rid of all of my errors and stuff. It's really annoying to edit, but I got rid of all of my stutters and made it really fluent. So you can really just go through and listen to the chapters like in your commute to work or like wherever. If in like 20, 30 minutes, get here, listen to the chapter back, and then you can read my notes over the chapter, and it's like a really good spark note in markdown format here, so you can just kind of get a really nice spark note over what the kind of meat and potatoes of the actual chapter was about, with some really good like in-text examples and screenshots and stuff. So if you're wanting, you know, these notes, these are really good. I think, tooting my own horn here, I think I would be, if I was like, I don't know, if I was learning, if I had something like this for chemistry when I was learning back in the day, rather than just grinding it myself alone, like it would have been really helpful. And so, yeah. Symmetrical. Oh, that was a bot. Hey, Blasto, welcome back in, dude. Linus allowed a couple of go-tos in the Linux kernel. Ooh, nice. I really want to like write some C code. I really am like enjoying the like creativity and like that you have with like a lot of these like it just seems like very open-ended. Like even like I don't know, like even more so than Python. Um just from the small little things I'm getting with printing and with um I don't know, like yes, it does rely on you to do more, but by you doing more, it gives you more freedom. So I don't know, maybe there's a toss up, more freedom has like more, issues later on with larger projects or whatnot. But like so far, I'm really liking how like I can really like specify like even on a more minute level these like print statements and like really have a lot of different ways to do these loops with all these different little decrement after or before the statement and or like these little things in C that you can do that you couldn't do in Python to just be a little bit more. I don't know. I don't know. It's kind of interesting. But anyways, I appreciate you guys being here and hanging out with me for today. Please like and subscribe if you are new and want to hang out with me on the daily. I've got a Discord link down below with the entire roadmap of my learning so far, from CS50 courses to books to my personal notes to personal projects, source code, all that kind of jazz. Everything's on my GitHub as well. So thank you guys so much for being here for today. We'll probably take tomorrow to go back through the notes and take a stab at the exercises. and keep going with our C programming and, keep going. Thank you guys so much for being here, and I'll see you tomorrow.